So now let's work in Z mod 13. It's really important to be able to do this without looking at a mod, a complete exponent table. But it's nice to sometimes go low tech and really confirm your work with that. And with small mods, you can actually build an exponent table or sometimes look in the book. Okay, so it's a good idea to think about, okay, how would I do this without having the mod 13 table sitting right here? Well, let's see, find four natural numbers m such that 2 to the m is equal to 1. Okay, well, when I've got something where I'm in a prime mod and I'm looking at some element of that, that modular arithmetic system to a power equals 1, we want to think about little Fermat, okay? And what we've got here is if you look at 2 to various powers, let's see. So these are all the k's, these are all the powers again, the exponents. And here's 2, and I'm raising to various powers. It starts out 4, 8, as you'd expect in ordinary integers, and then starts wrapping around. 16 is equivalent to 3. Then you double again in a normal way to 6. You double again in a normal way to 12. But now when you double again, it's going to wrap around again. 2 times 12 is 24. That's equivalent to 11. And so sometimes for small numbers, it happens to just look normally. Oh, 5 doubles to 10. But whenever it wraps around, somebody who doesn't know mods or doesn't know it's mod 13 is going to be like, what are you doing? Okay. Now, of course, what we see is if I look at all the powers of 2 in this list, only 2 to the 12 seems to work. Right? So we've got 2 to the 12 equals 1. And that's, of course, exactly what little Fermat says. But it's saying find 4 of them. Okay. Well, okay. Now, there's one really kind of silly one, which we might as well put in. 0. Now, the way the book states this is natural numbers, and they don't consider 0 to be a natural number. That's a little unusual in modern usage. So I would accept 0 as something. Anything to the 0 is going to be equal to 1. Okay, so that's something I would accept. But what else? Even if you accept 0, there's still 2 more we want to find. Well, it's very similar to what we were doing before. If you look at beyond what this table has, you can keep going. K equals 14, K equals 15, K equals 16, down, down, down. Well, what's going to happen, though? It's going to start repeating. The 13 row is exactly just the K equals 1 row, which is basically up here, just A itself. And then it's going to replicate the K equals 2 row, etc. And just like in the previous part, what we're going to get is, for example, 2 to the 24 is just the same as, let's see, let me copy that, paste it. It's just 2 to the 12th times 2 to the 12th. I know the cursor's right in the front of it, sorry. Is just going to be 1 again, okay? And we can continue in the same vein. 2 to the 36, that's going to equal 1, okay? So what those exponents have in common is I'm pretty much forced to use, I must use an m that is a multiple of 12, which it's no accident that's 13 minus 1. Okay, so what about 2 bar to the m equals 2? I'm just going to stop saying the bar. So 2 to the m equals 2. Well, obviously 1 works. Okay. So here m equals 1 works from the table. That's just this row here, k equals 1 row. That's a itself. And right at the bottom, k equals 13 works. And then it's the same deal. If I multiply by a to the 12th, in other words, I raise the exponent up by 12, I add 12 to the exponent to get 25, that's going to work as well. Okay, so again, it's just all mod 12. And so 37, 49, you could get boring after this. And so there's various ways to express that, but the most sophisticated way is that these are exactly the congruence class of 1 mod 12. So again, it's really cool that the exponent behavior has its own mod behavior, but it's mod 12 and not mod 13. Okay, so they're all the things that are congruent to 1 mod 12. In fact, if you wanted to go beyond natural numbers, I claim that m equals minus 11 also works. Okay, we haven't necessarily focused on that, but I claim that if you take 2 to the minus 11 in mod 13, then it'll actually work as well. We'll see if we need to focus on that later. Okay. Okay, what about 2 to the m equals 4? Okay, I'm going to go through this pretty quickly. Well, obviously 2, because 2 to the 2 in ordinary integers works, but then add 12 again, add 12 again, and this is just exactly the integers that are congruent to 2 mod 12. Okay. So I want to put in one more. This is something that the books version, I basically just did a book problem here. It's problem 8. But I'm putting in one more thing. What about, this is all about 2 raised to various powers. And one thing you notice about the 2 column here is that you don't get a 1 unexpectedly. The 1 here in the k equals 12 row has to be there by little Fermat. It's one of the deepest things in all of mathematics. Wonderfully significant. But there's no, it doesn't get back to 1 prematurely. But look at 3. Look at the 3 column. It actually gets back to 1 quite a bit earlier than little Fermat says it has to. 3 to the 3, of course, is 9, and mod 13 that doesn't affect the 9 there. But then you multiply by 3, 27 mod 13 is congruent to 1. And then, of course, once you've got a 1, the cycle will start over much more quickly. Then you triple it to get 3. You triple it to get 9. You triple 9, you're not going to get a different answer. It's going to be 1. Triple, triple, triple. So it's just if you started with a to the 0, for example, it'd be 139, 139, 139, 139, 139, 139. So it actually repeats faster. Okay. So in particular, what we've got here is m equals, and I'm going to put in the 0, not that the book would want that, and then 3, and then 6, and then 9, and then 12, and then 15, and then 18, and then 21, Okay, so it actually repeats faster, right? So these repeat with a period of 3, which is different from the 12 repetition that we saw before. But notice that 3 does divide into 12. And here's why it has to be true. It still has to sync up at the k equals 12 row, right? Suppose the 3 pattern were repeating every 5. And so like at 5 you got a 1, and then at 10 you got a 1. Then it would not work with the 12 row. Okay, and so what's more general is that in general, the repetition has to repeat with a period that divides the mod minus 1. The original mod that we're working in. So that's a little contrast that you can get some 1s. There's some 1s in this table over here that aren't guaranteed by little Fermat. But if you notice where they are, there's some 1s in the 3 row, the 4 row, the 6 row, and the 8 row, the 9 row, the 10 row. But apart, of course, from 1 to anything, which is a stupid, there's no like 1s in the 5 row besides 1 to the something, 1 to the 5. And that's not an accident, because if you got a 1 here, that would repeat with the wrong period. Okay, so that's just a little extra little tidbit, which is kind of cool. It gets very significant later when you do more sophisticated theory with this stuff.